Okay, welcome to my channel everyone. My name is Ansa, your helping hand, and in today's video we're going to be going through a question, an exam question specifically that has to do with the binomial distribution and specifically the normal approximation to the binomial distribution. Okay, so the way this video is going to work is basically I'll show you the question and then hopefully you'll pause and try and do it on your own and then come back to the video, unpause, and then I'll work through the answer. So these questions and most of the questions that I will be doing will all come from the Institute and Faculty of Actuaries past papers. So the IFoA, they are the professional body for actuaries in the UK, and their curriculum and the South African actuarial curriculum are kind of goes hand in hand, especially at the lower levels of the exams. And yeah, and we obviously, as a stats department, we have to hopefully our stats department is still accredited with us after this whole pandemic, but basically because as a department we have to have that level of quality of education, that standard of work, it would be roughly equivalent to the UK standard of questions. So that's why I think that using the IFoA questions is a good baseline for practicing for your exams. And also it teaches you to kind of think out of the box a little bit in terms of not just using, not just doing rote examples of like doing the exact same thing over and over, and where all of your information is given to you, you kind of have to think a little bit more. Okay, so now we're going to get to the question. So this is from 2016 September exam question 3. So an insurance company has a portfolio of 10,000 policies. Based on past data, the company estimates that the probability of a claim on any one policy in a year is 0.03. It assumes no policy will generate more than one claim in a year. So you have to determine the approximate probability of more than 40 claims from the portfolio of 10,000 policies in a year. Question 2, or II, determine an approximate equal-tailed interval into which the number of claims per year will fall with probability 0.95. And then in practice, 42 claims were received during a particular year. The director of the company complains about the range of estimates in part 2 being wrong. Comment on the director's complaint. Okay, so I've read through the question. I'm going to pause and let you do your thing, and then you can come back when you are ready. Okay, so I'm assuming that you've paused and you've tried going about answering this. So the basic understanding of the first part of the question without the information in the question, at least without going through what the question is asking you to do, is we have this insurance company and they have a portfolio of 10,000 policies. So essentially we're thinking of N as being 10,000. So each policy is an independent trial, and we're thinking about success in this term as generating one claim, right, or generating a claim. So P is the probability that a policy will claim, right? So essentially, we do actually have a binomial distribution. If we call X the number of claims that we get in a particular year, right, this will be binomial, right, 10,000 and 0.003. Okay, now for question 1, they're asking you to determine, and this is important, the approximate probability. So they're not saying an exact probability, right? So they're not asking you to do a sum, because if they didn't say approximate, or if they said exact and you had to do the probability of more than 40 claims, well, you would be doing the probability that X is greater than 40, and because if they were asking for an exact probability, you would have to go from I is equal to 40 to 10,000 I, P to the power of I, Q to the power of 10,000 minus I, and you would have to do that for 9,960 sums. And if you don't have a computer, that's difficult. So, and in an exam, you don't really have a computer. Well, some of the exams you do, but that's besides the point. In this one, I don't think you do. So essentially, that's why they're asking for the approximate probability, and it's also just a test that you understand the normal approximation. So because our n is 10,000, right? Our n is incredibly large. Obviously, our p is a bit it's quite small. Like it's a lot closer to 1. I mean, it's a lot closer to 0 than it is to 0.5. But because we've got this 10,000 here, right, we have quite a large number of trials. So essentially, the approximation can still work. And we would check that by either doing np is greater than or equal to 10, which if you did do that, you'd be taking 10,000 multiplied by 0.03, and that's equal to 30, and that is greater than 10. So the most basic form of the normal approximation, or the most basic rule of thumb, says we can actually use this approximation. We could also do the more advanced one where we're looking at 9 times, and then we'd have to do 1 minus p over p, which is the same thing as 9 times 0.997 over 0.03. And if you did that in a calculator, you'd see that that's 0.997 over 3 multiplied by 9. That's equal to, sorry, that should be 0.003. That's equal to 2,991. Right, so our n here is 10,000 and it is greater than 2,991. So this approximation will work. So we can therefore say by the CLT, x is approximately normal, where our n value is our mu value would be np. So we're going to take 10,000 multiplied by 0.0003, and you're going to get 30. And then your variance would be 29.91. I've kind of worked all of these things out already, but obviously you can go ahead and do it. So this is our approximation here, right? So if we're looking at the probability that x is greater than, we're asking for whether x is greater than or equal to 40, right? When we use a binomial distribution, it's that all that sums, but when we're using a normal distribution, it's a lot easier to calculate. And we do have to do the continuity correction because, as we saw in the video about using the normal approximation, that the continuity correction always makes your approximation better. So we need to think about whether we're adding or subtracting. And the way I like to think about it is, well, if we have this is here is 40, remember we had the rule, there's multiple ways you can think about it, but the most basic understanding is that when we're doing a strict inequality, this approximation will always overshoot, so we need to subtract area. So essentially this over here, this greater than area, is always going to be more than our actual probability, so we need to subtract area. So when we subtract area, we're going to be adding 0.5 to our bound. So this is the probability is approximately that x is greater than 40.5. And then we just standardize it. So we're going to take x minus 30 over the square root of 29.91 is greater than 40.5 minus 30 over the square root of 29.91. And that's approximately that z, right? Z is a standard normal. Z is a standard normal. So because we've standardized our x, we can use a standard normal, and then we just need this, what's called a z-score, and that's going to be equal to 1.91991, and you can add more decimal places, but essentially once you're doing that, oh, sorry, I've realized that I suddenly have a equal to sign here. That shouldn't be there. But it doesn't really matter in the normal case because it's a continuous distribution, so doesn't matter. Anyway, now we find this, now we have this z-score, where this is 1.91991, and obviously to calculate that, you just need to look at your tables, look at your, however you calculate your normal distributions, and when you do that probability, you'll get that it's equal to 0.02743457232325585. I'm just reading off the exact long number that I have from RStudio. So that's going to be equal to 0.02 7, basically, if you're doing to 3 decimal places. I'm not entirely sure what the IFoA policy is with decimals, but whatever your particular policy is, just obviously just round that number to it. So that's the probability for question I. That's the answer for question I. So at this point, if you are not interested in confidence intervals or you haven't learned about confidence intervals, then you can just stop the video and that's the end of the video. But I am going to do question 2 just because it's not difficult to understand what the question is asking. And so I'm going to do it, and you can watch the video if you are interested in it. Or if you have learned about confidence intervals and you want to practice them. Otherwise, just stop the video, and don't forget to like and subscribe and comment if you are interested in other things, or comment if you want requests or other things like that. So anyway, question 2. Question 2 says, determine an approximate equal-tailed interval into which the number of claims per year will fall with probability 0.95. So the kind of basic understanding of this question is we've got this X thing, right, that looks normal, right? We need to find some interval, some A and B, right? This is our X values, right? Our X values can be anything, but we need to find it so that the probability that X is going to be in this range, right, that we're going to find an X here. So the probability that X is in this range, and we could put equal signs, doesn't matter, is equal to 0.95. Now, they mention equal-tailed intervals, and all that means is just that we want 0.95 in the middle, and we want everything on the ends, right, the extreme values, to be equally likely. So this area over here needs to be equal to this area over here. So those two areas are equal, and obviously if this is 0.95, this is 0.025, and this is 0.025, so that when you add them up together, they get 0.5, which is 5%, and when you add that to 0.95, you get 100%, which is 1. So that's all of your probability. So now we're just trying to find this range A and B where this is the case, and we could do it when X is this normal where X is this binomial distribution, right? I think you could do that technically. Haven't really tried, but doing that is very difficult, like we said. So we approximate it, and we say this is approximately a normal distribution with 30 and 29.91. And so even this normal distribution, finding these A and B values where you have 95% is not that easy, but it's a lot easier with a standard normal because you can find, what the quantiles are that give you 0.25 to the right and 0.25 to the left. So we standardize it. So we say, okay, the probability that A is less than or equal to this thing, B, we just standardize. We standardize our X, which means we take X, we subtract our mean, divide by our variance, 29.91. That's less than or equal to, and we're going to have to do the same thing to these values A and B. But all we're going to be doing is we're going to be subtracting and multiplying a particular constant. We're finding this constants A and B. So I'm just going to call them C and D for now, because we'll work them out later, where C is equal to A minus 30 over square root of 29.91, and D is equal to B minus 30 over square root of 29.91. So that's just these two things. And now we have this probability that our Z value, because we've now standardized our X, is less than or equal to D, is less than or equal to C, and we want that to be 95%. So it's the same idea. We're finding C, we're finding D, so that our Z score, where this is Z, is a normal with 0.1. This area over here is 0.95, 0.25, and 0.25 as well. So that's essentially what we're doing. And so what you need to go and do is you need to go and find what value of what Z score, or what Z quantile essentially has 0.295 to the right, okay, and what quantile has 0.025 to the left, right? 0.025 being your probability. So you can go and do that, and essentially this will come out to being 1.96, and C will be negative 1.96. There's a lot more decimal places, and I would advise that you keep those decimal places somewhere in your calculator. And so now we can figure out so now we know what D and C is, right, using our table. So you'd go to your table, you would find the probability to the right of being 0.25 and find that quantile, and you'd find the probability, the quantile where you have 0.025 to the left, and you'd find D and C. And now we can go and find A and B because we defined what C and D are in terms of A and B. So D is going to be equal to B minus 30 over square root of 29.91, and that's equal to 1.96. So that means that B is equal to, well, multiply and add the 30, so 30 plus 1.96 times by 29.91. And when you go and do this in a calculator or on your computer, however you want to do it, you're going to get 40.72. And for C, right, C is equal to A minus 30 over square root of 29.91, and that's equal to negative 1.96. So therefore A is equal to 30 minus 1.96 times 29.91, and you get that A is equal to 19.28. So now we have this probability that X is less than or equal to 40.72 and 19.28. That probability is 0.95. So basically what we've created is this interval, right? So X is in the interval 19.28 and 40.72, right? That interval, right, your X value, the number of claims that you have in a year, 95% of the time, or with 95% probability, your X will fall into that interval, right? And that's what a confidence interval basically is, right? So now, oops, sorry, I'll just undo that little scribble. So now if you look at question 3, where they're saying in practice 42 claims were received in a particular year, so it's outside of that range of 40.72, right? 42 claims were received in a particular year, and the director of the company complains that your range of estimates were wrong. So you need to comment on the director's complaint. Well, your complaint is that we aren't saying that that your X value will always be in this interval, just that your X value will be in this interval 95% of the time. And so there's a 5% probability that your X value in a particular year will not be in that interval. And so that's how the confidence interval basically works. And that is basically your comment that you have to make, that, well, the director doesn't understand what this confidence interval is. Obviously, you'd be a bit more polite than that. But yeah, that's the end of the question. And don't forget to like and subscribe if you liked the video, and comment if you have any questions or requests. And yeah, I'll see you in the next video. Bye.